The title is conformal measures for conformal dynamics.
Thank you very much, Felix. I would like to thank Felix, Artem, and all the organizers of the seminar to invite me to hear the seminar today and giving me the opportunity to speak. It's my great pleasure to be at IMPAN all the time. I was here countless times, but it's again good to speak. I would like also to thank Professor Andras Dunik for inviting me to Warsaw, and I will be speaking about conformal measures for conformal dynamics. This will be just kind of survey lecture, not very technical, and I will speak how conformal measures can be used in various areas of dynamical systems that exhibit some actually conformal features, and how conformal measures that are dynamically defined help to understand geometry of sets, primarily Hausdorff dimensions, and even more importantly, Hausdorff measures. Maybe more Hausdorff measures and packing measures, or geometric measures. This will be the goal, that conformal measure is a tool to understand geometry. So let me give some history. So I think it first came from the work of Henri Lebesgue, who introduced actually what we know now Lebesgue measure, and got this change of variable formulas. Actually, this really would go first to probably the fundamental theorem of calculus, where conformality was used. All maps on the in dimension 1 are conformal, but are differentiable. So, so then here is like the formula for the. I don't think that Hausdorff came up with this formula, but this was just almost immediate after he defined the concept of what we know now Hausdorff measures. And in dynamics, it started with the seminal work of Samuel Patterson, who introduced conformal measures in the context of Fuchsian groups. So Kleinian groups acting just on the unit disk, and he defined conformal measure in an axiomatic way by demanding that this equality holds with some Borel probability measure on the limit set, and delta being just an exponent.
For all G in the
Sorry?
For all G.
For all G and for all A. Okay?
For all A.
And for all A, for conformal, for Fuchsian groups, this is for all A, because all the maps are actually are univalent, right? So this is you do not have to do restrictions. And then Dennis Sullivan actually extended Patterson definition to all Kleinian groups. So this group acting on the unit disk, acting as isometries with respect to the Poincare metric, and then Dennis Sullivan also introduced this definition to rational functions acting on the unit sphere by actually the same formula. However, as Sven pointed out, here one should restrict the range of the sets A by requiring that the map restricted to them is 1-to-1. So this is, of course, Borel and so on, and so on. So this is the most, the first history of conformal measures. And the name of conformal measure was coined by Samuel Patterson. So let me now give. Okay, let me give some history, some history of work. These are some selected papers. Let's see. Okay. some selected papers. So first Patterson, 1976, then where he introduced the concept, used it to study house of measure. Then there is a nice Patterson survey lectures on the limit set of Kleinian groups. This is already after Sullivan came up with his definition. This is the paper of Sullivan, and he wrote it in several papers, proving various geometric and dynamical properties. Then more recently, some Velani's work, Stratman, and Denker Stratman wrote about it. And then conformal measure for rational functions. I think that this really started in these papers. Felix, is it correct? I think yes, this is where Sullivan introduced them already. This seminar, his preprint, was very influential, in particular in Warsaw. And Sullivan then myself.
Notes, or maybe preparation.
I think this was
the
the
notes on lectures by Sullivan, by Baker and C.
And C, yes. So then we studied conformal measures, trying to understand what is really the exponent in the case of rational functions. I will be talking about it, and so then also some other papers here for rational functions, and we gave with Felix a quite nice, I think, a chapter on conformal measures and in relation to Pearson theory, Katek theory, and so on. So to be sure, I will be speaking really about these classical conformal measures, not more general conformal measures, but are actually eigenmeasure of the dual of the parent-Frobenius operator. There's huge also field, but I will not speaking about this here. So then most recent, I think, survey about this and approach is in the first volume of my book with Sarah Monday and Mario Roy, where we treated them at length. And so then for transcendental dynamics, I think conformal measures in transcendental dynamics the first time came with the work of Krzysztof Mariusz in 1995, where he studied it. He introduced them to study geometry of limit set of the tangent family. And the picture which he came up with was very similar to the picture which holds for parabolic rational functions. Then we somehow, with Janina Kotus, extended Krzysztof Urbański work. Then there were papers with Anna Zdunik for exponential family. And this is here after that, maybe my paper with Volker Meyer, where we actually covered quite large class of functions, of transcendental functions by means of changing of singular change of Riemannian metric on the plane. Because if you want to define, for example, for exponential function, ordinary parent-Frobenius operator, then you come up with infinite series, and it's impossible. But if you change in Anna Zdunik, we projected it on the cylinder. This was one way, but this was restricted only to somehow periodic functions. But with Volker Meyer, we introduced singular change of metric and covered much bigger class of functions. And then, let's see. So this is more works. So then Barański, Karpińska, and Zdunik proved some general version of Bayes' formula, which is related to conformal measures. And they also studied conformal measures. And Meyer and Zdunik actually shown that there are transcendental functions for which no conformal measure exists. So
I didn't understand. what exists or not exists.
So the failure. Okay, this is written the failure of Ruel's property. So this paper has Ruel's property. Okay, they meant that even in the analytic family, that hyperbolic causal dimensions doesn't have to behave in the analytic way. Okay, but they also proved that conformal measure does not exist.
There must be some bifurcations.
Right. Yes. Okay. So then also maybe more recently with Janina Kotus we treated elliptic functions. So this is about the rational functions, transcendental functions, and okay. Don't I have it here? Maybe I didn't copy.
So this shows that
Blank.
it's blank.
Yeah, here is blank. Maybe blank. So then I will go to my laptop. So.
Can you see anything over there, or?
Yes.
It's blank.
Is that on here? So then a moment.
Yes, it shows blank pages starting.
So then blank pages.
So it might be. So let me try to reopen it. So where was it?
Right.
For some reason, Adobe did not. I see. The problem that was on your.
Yes.
So I need to copy it on a laptop. A moment. So where was it?
Lectures.
I see. Okay.
Lesson 25 and.
Let me just copy it.
Oh, this is different. Okay. This is soon. This could.
49.
Oh no, this is not this way. This I gave somewhere else.
I see.
But this,
Okay.
the one now is. Okay, go to lectures 2025. Okay, the first one.
Okay.
And then infant. Okay, and this one.
This one is correct?
Yes.
Okay.
Let's hope it has all the pages.
So this one is correct. September 16.
Okay, yes, we have. Yes, yes.
One moment.
Dziękuję bardzo.
This looks.
Dobrze. Okay, another topic I would like to talk about is iterated, conformal iterated function systems that were okay, and the idea is to have countable alphabet, and countable alphabet, they were introduced in 1996 by Daniel Malvin and myself. They stemmed from a linear iterated function system, linear similarity function system, where the seminal work was due to Hutchinson and then later on Tim Bedford. And here is a bunch of papers and the book with Daniel Malvin, a paper with Tomasz Szarek, and okay, these are the papers about continuity of Hausdorff measures with Tomasz Szarek and Anna Zunik. So I will be speaking about it, and when I speak about continuity of Hausdorff measures, where conformal measures plays an important role, I mean numerical value of conformal measure, not normalized. And then Kariuri has something. This is the work with Anna Zdunik, and we generalized it with Vasilis Housionis and Jeremy Tyson to graph on the Carnot groups and even more general groups, and with now Rafał Tryniecki and Zdunik about exact asymptotic of Hausdorff measures for continued fractions with bounded entries. So, okay, so this will be these topics. Kleinian groups, rational functions, transcendental, meromorphic functions, and iterated function systems, or somewhat more generally graph-directed Markov systems, but I really, the most important theorems will be formulated for iterated function systems. So, okay, so let's start with some definitions. Okay, first, Fuchsian and Kleinian groups. So we have a unit ball, Poincare metric, and I think the most important object introduced in this theory, where everything starts with, is the Poincare series. So you pick a positive number and fix any 2 points x and y in the open unit ball and look at this Poincare series. And then the second number, which is defined purely in dynamical terms, and it has actually nothing to do with geometry a priori, is the Poincare exponent, which is the infimum of such numbers S that the Poincare series converges. By geometrical considerations, it is possible to show that it is always less than or equal than the dimension of the ambient space. And this exponent does not depend on the choice of x and y, it's independent of that. And so this exponent has then the geometrical interpretation. So let's say, so each non-zero finite Hausdorff packing measure is conformal. So if you have such Poincare disk, a Poincare ball, and you have limit set, and you take a Hausdorff measure and conformal measure, and they are both, if they happen to be positive and finite, then they are conformal, meaning that they satisfy this property that the measure of the image is equal to the measure of the image of G delta of A is equal to the integral over A G derivative G prime delta dm delta dm. So if you normalize it, the divide, then you will get probability measures. So packing measure, actually Hausdorff measure is certainly well known. Packing measure may be a little bit less known. It was introduced, this is the dual concept to Hausdorff measure. It was introduced in the late 1980s by Claude Tricot, James Taylor, and Dennis Sullivan. Sullivan independently of Tricot and Taylor. And for Hausdorff measure, we want to take as economical as possible coverings, while for defining packing measure, we look at the packings and try to them also try to pack as economically as possible. So both measures are actually very good. Both measures serve to study geometrical properties of sets, and sometimes they are equal, or or at least one is a multiple of the other. And then you can define packing dimension also in the same way as how the dimension is defined by looking at the parameter where the value being first infinity becomes then 0. And a central concept goal of having conformal measure is to understand geometric measure, Hausdorff packing. Okay, the key idea in all of that is to look at this ratio, measure with respect the ratio of the measure over the radius to the power h. And it can behave in any way. However, if it behaves such that this ratio is bounded above uniformly with respect to r being, for example, taking values from 0 to 1, and is bounded from below, then this measure is called R-force measures, and then the geometry is really very regular, very nice. First of all, the packing, the Hausdorff and packing measures are positive and finite in this dimension, and both are equivalent to the measure m. Secondly, all fractal dimensions, Hausdorff packing, box canting, are equal to h. If you are also familiar with as-1 dimension, the situation is, I think, more subtle. Just Alfred's property is not sufficient to claim that the as-1 dimension is equal to h. And this is the case when we have Alfred's measures for convex co-compact Kleinian groups, finite alphabet conformal iterated function systems, expanding, some expanding, and some more rational functions. Okay, so maybe just theorem. If you have if G is a Kleinian group acting on Bn and delta G is the Poincare exponent, then there exists a probability measure supported on the limit set. So this is so such a measure exists, and it is constructed in a very explicit way. I will show the conformal measures are not usually unique, and even exponent is not unique. Okay? And however, if we have a convex co-compact Kleinian group, then the situation is as best as possible, meaning that the conformal measure has the Alfred's property, and all the dimensions, Hausdorff packing, box canting, both box canting and upper box canting and lower box canting dimension exist, are equal, and all of them are equal to the Poincare exponent and are smaller than the dimension of the ambient unit ball. And then also, this is already even beyond. This does not really follow. This last property does not follow from Alfred's property alone. You really have to use dynamics, and that all of them are equal. And in particular, it follows from this property that if you take the normalized conformal measure, so then it is unique. So in this case, the normalized conformal measure in this dimension is unique, and there are no measure in any other dimension. Yes?
Question. So this measure M delta is supported on the
Limit
limit
set.
set.
Yes.
Kind of on the boundary, right?
Right, on the limit set, yes.
So it will be automatic kind of dimension less or equal to n minus 1
Yes.
or something?
Yes. Yes. Oh, okay. Yes. Yes. Oh, yeah, okay, so you mean, okay, Bn, you mean, but this is, right, but yes, right, so actually, this is a good point. You should say that if the ball is dimension n, so then the, okay, so then the dimension is, let's see, the dimension of the sphere is n minus 1, and the dimension of the limit set should be, yes, is less than n minus 1. Okay, that's right. So that's this, and let's see. Okay, and if G is a finite, is geometrically finite Kleinian group acting on the n, geometrically finite roughly means that there exists a fundamental domain which is actually a polyhedron, a hyperbolic polyhedron having finitely many actually walls. Then,
Excuse me, I have a question from online audience.
yes.
Polina wants to clarify. She says that Kleinian groups act on three-dimensional space. So she was asking
On what? On
three-dimensional space.
Okay, Kleinian, okay, this depends on the terminology. I understand Kleinian groups acting on n-dimensional space. If she doesn't like Kleinian, she may think about it just a discrete group with respect to the Poincare metric. Okay. So acting on any dimension, even actually it's possible to consider acting on Hilbert spaces, and even on some other say Gromov spaces. And Hilbert space is particularly difficult because these maps are not proper. Okay, so there's any dimension, not only three dimension. Okay. And so here either the situation is the same as for convex co-compact groups, or Hausdorff measure.
Excuse me, sorry for interrupting.
Yes.
We have a further question. Could you please show again the definition of the Poincare metric?
Oh, Poincare metric. Okay, if I remember, Poincare metric is okay. I think Poincare metric is just a dz over 1 minus sum from k equal 1 to n, okay, zk squared, and I think here is to the power 1 half, or all of this is to the power 1/2. This is the Poincare metric. So Riemann metric, and then it gives rise to the length of curves and to the ordinary metric. So I think this should be n minus 1. So if G is a Kleinian group acting on Bn, I think this is here should be n minus 1. Then how the dimension is equal to n minus 1 if and only if G is not geometrically finite. So if G is not geometrically finite, but is actually should be finitely generated, then dimension is smaller than n, then dimension is already n minus 1 is full. So okay. So now maybe just a short sketch of the Patterson-Sullivan construction of conformal measure. If the Kleinian groups are divided in two classes of convergence type and of divergence type. Depending on divergence type means that for each s bigger than the Poincare exponent, this series, okay, convergence time that at this moment, at this moment, this is infinite. So if this is divergence, it's finite. If this is divergence time, so for every s bigger than delta g, this series diverges, and then we look at the normalized measures, living on the not living on the limit set, but living on orbits of the say of 0 in this case, and closer closer and closer to the closer to the boundary, and the limit you get conformal measure with the Poincare exponent. So any such limit is a conformal measure, and if the group is of convergence type, then this series here, then this series. Okay, so this is the point here that if the group is divergent, if the series is delta s divergent at delta s, then the graph of the functions sigma s looks like this, and then if s approaches delta s, then the denominator here becomes bigger and bigger, and as a limit you will get indeed a measure on the limit set. So this property fails in the case of convergence type, where the graph looks somehow like that, and then you can still would get a limit measure, but it would be supported on inside. So the Patterson came up with the method to make this convergent series divergent. Namely, he considered slowly varying functions satisfying this property and looked at such generalized Poincare series. This function is by no means unique, non-canonical, and then looked so that this series becomes becomes divergent, and then the limit is the limit measure lives on the limit set. And again, in this case, this is we get conformal measure. So this is just a rough construction. Okay, so maybe okay. So now I would like now to speak about conformal measures for iterated function systems and graph-directed Markov systems. So existence and unique starts actually for countable alphabet with our work, my work with Dan Moldin, and here, this may be the definition of the graph-directed Markov systems. So this basically means that we have a bunch of sets, and maps between them, and we start iterating, going from one space to the other, and iteration is allowed if the incidence matrix allows you to do it. And then this family of maps is actually they are uniform contractions. So all with Lipschitz constants less than or equal to beta, and this is called iterated function systems. So they are conformal. So no conformality here. Just this. This is well known, I think, definition. And a graph-directed system is called maximal if the incidence matrix is as full as possible. So whenever you can do iterate, you really do it. Incidence matrix in general may permit you, but although here is a map, you may not be allowed to use it in the iterations because the value is 0. And a graph-directed Markov system is called an iterated function system if the set of vertices, vertices are parameterized, these sets is just a singleton, and the matrix is full. So this is the case where we have just one space and we have a bunch of maps and maybe infinitely many, and all of them are possible. So let me just give two examples of iterated function systems. One which is phi1 of x is equal to x over 2, and phi2 of x is equal to, what it should be, I think, x plus 1 over 2, okay, finite, it was very simple. And the other one is where we have infinitely many, phi n of x is equal to 1 over x plus n. This one is on the interval 0, 1. You recognize that these are just what? The inverse branches of the Gauss map. Okay?
Excuse me, Mariusz, just to check, you don't assume that the image is not a person?
Not yet. Not yet. Not in this definition. Not yet. Okay? This open set condition, what you mean, and this will be assumed. Yes, when we come to conformal. So this is its maximal directed set. Okay, whose is singleton. And so, just I would like to say in the limit set. So you take a word in the let's see, in the coding in the coding space, and you start iterate them from back to forth in this way. So in such a way, I'm getting a family of compact and descending sets. And this intersection is therefore not empty, and since the diameters converge to 0 and even exponentially fast, which is not important at the moment, the singleton is this intersection is the singleton, and its only element is defined by is denoted by pi of omega. This is the projection map from the coding space to to the disjoint topological union of these sets. And the limit set is image of under this projection. So, now, if the alphabet is finite, the limit set is always compact as the image of a continuous map of a compact space. If the alphabet is infinite, the limit set needs not be compact. I do not look at the closure of the limit set, I look at the limit set. So, for example, what is the limit set for these two maps? This is the interval 0, 1. The interval 0, 1 is the perfect fractal set, and in this case, what is the limit set? I will be talking about it later, but this is just a set of irrational numbers of the interval 0, 1. It's not only these numbers have continuous fraction expansion in infinite way. So, okay, and in general, the limit set, I think, need not be Borel, but it has to be, I think, analytic set and so on. It is analytic set by definition. So, so this project, the set is called the limit set or attractor. And now comes what Artem mentioned. I'm talking about conformal iterated function system. So now the maps are conformal. Okay, the maps are conformal, and this is the no overlap condition. So this weak no overlap condition is open set condition. I will not speak about iterated function system with overlaps, which is an area in itself, very nice, very beautiful, has its noun result, has its noun results, method, and so on. So, and I assume also this distortion is stronger version of the distortion property for conformal maps. Okay, I would like just to comment that this distortion property, do I have something about it? No. But the distortion property is usually automatic. You do not have to assume it. If the dimension is greater than or equal to 3, then it easily follows from all these assumptions and Lewis and Liouville representation theorem. If the dimension is greater than or equal to 2, then it follows basically from Kebbe's distortion theorem for maps and anti-holomorphic maps. And if dimension is 1, then all differentiable maps are conformal. And if they are actually, let's see, C1 plus epsilon. If they are C1 plus epsilon, then this distortion holds because of dynamical reasons. If the alphabet is infinite, then there's maybe potential problem because we don't have immediate tools, and then you can use either dynamical method for the particular system, or, for example, for this system, which is on the interval 0, 1, we know that distortion holds immediately because all these maps can be extended to some open disks containing 0, 1, and this disk comes into itself and you have a distortion theorem. This would be one way. Okay. So now the basic concept here in this theory is topological pressure, which is this limit, very natural. Of this limit exists because this sequence log of the sum is sub-additive, and there is one also other number, which is theta number, which is infimum of such t, but the pressure is finite. This number is quite interesting, and I will talk about it for a moment. So maybe next slide. Just topological pressure is finite if and only if the first level sums are finite. So you do not have to do any iteration, you just look at this. And B, this infimum of such t greater than or equal to 0, where the pressure was finite, is just when this first level set is finite. This is the number theta s. I again say whether you do not have to look at at higher iterates. And the topological pressure function, which basically looks in the same way, somewhat in the same way as I drew here, but has the following property: is not increasing on the interval 0 infinity, okay, strictly decreasing on here should be theta. Strictly decreasing on theta through positive infinity, and because here is so just is all the time infinity, and is convex and continuous, even real analytic, and P0 of P of 0 is infinity if and only if the alphabet is infinite. So these are numbers, and now using conformal measures, we can prove the following version of the balance formula. But we define the number Hs, which is infimum of such t that pressure is less than or equal to 0, and then pressure at this value is less than or equal to 0, and if some t exists for which pressure is 0, then this is equal to H. And then Hausdorff balance formula, which we proved with Dan Moldin, is that Hausdorff dimension is that this number Hs is equal to the Hausdorff dimension of the whole limit set, not of the closure of the limit set, not necessarily, but of the limit set. And this is supremum of Hausdorff dimensions over all sets, over all finite subsets. And this number, it can be also proved, is greater than or equal to theta of S. So in particular, Hausdorff dimension is greater than or equal to theta of S. Okay, so now, if the alphabet is finite, then the number theta of S is of course negative infinity, and this is nothing. Right? If alphabet, for example, but if I have already this system, then for this system, theta number is clearly seen to be equal to what? Is 1/2. Because, and if this is 1/2, we get immediately that the Hausdorff dimension is bigger than 1/2. This is still actually obvious, because we know that this is equal to 1, but for many other iterated function systems, it gives really quite nice information, lower bound, almost actually for free. With no raw work, with no iteration needed, you get lower bound. We particularly use it very heavily with Janina Kotus to estimate Hausdorff dimension from below of the limit set of elliptic functions by constructing some appropriate iterated function system within the Julia set. So this is a very helpful formula. Okay, and now here is about conformal measure may not exist. Okay, moment, do I have? No, okay, excuse this. So conformal measure exists okay, if and only if the following properties holds. So usually, so for iterated function systems, conformal measure may exist or may not. So if S is finitely reducible, conformal direct Markov system satisfying a strong open set condition, then conformal measure exists if and only if pressure is equal to 0, and moreover, then the conformal measure is unique. And the system is called irregular, is then called irregular, and all finite systems are regular, and irregular infinite systems do exist. So there exist conformal iterated function systems for which actually no conformal measure exists, and this is something unlike, for example, the theory of Kleinian groups, where conformal measures always exist. Okay? This construction is not so difficult. This is of such system, of such irregular system is linear on the interval 0, 1. And construction of conformal measures here is just, the best one is via countable alphabet, thermodynamic formalism, a projection of the eigenmeasure of the dual operator. And then this conformal measure permits us to understand Hausdorff measure. If the system is finitely irreducible, and then the Hausdorff measure is finite. If in addition the system is regular, then Hausdorff measure is absolutely continuous with respect to the conformal measure. Okay, and radon-Nikodym derivative is uniformly bounded away. If Hausdorff measure is finite, in addition, then the normalized Hausdorff measure is the conformal measure, and it is unique. And if the alphabet is finite, then this property always holds and conformal measure exists. And this is assuming this open set condition. So now, okay, we can also say something about packing measure. So if the system satisfies strong open set condition, then conformal measure, just the opposite holds. Conformal measure is absolutely continuous with respect to the packing measure, and if the if A holds, then packing measure is always positive. And if packing measure is finite, then normalized packing measure is the conformal measure, and if the alphabet is finite, then the conformal measure is Alfors measures, and both packing measure and conformal measures are packing measure and Hausdorff measures are multiple of each other. So, and there are examples where a Hausdorff measure is neither packing nor Hausdorff, and this is also like for Kleinian groups. So now let me speak more about this system which I already introduced, this Gauss system, giving bar such maps on the interval 0, 1, and these are just holomorphic inverse branches of the Gauss map, and JG is the limit set, and the projection map from the coding space is given by the continued fraction expansion. So, okay, therefore, for example, immediately we see that all the limit sets are the limit set consists of irrational numbers.
Before you needed contraction.
Sorry?
You needed contraction or parabolic.
No, okay. Yes, yeah. 0, okay, if you take 1 over x plus 1, then derivative at 0 is 1. Yes. That's right. But this is not a fixed point, and if you pass to the second iterate, then already all the derivatives are less than 1. Yes, so technically it does not fit. So in the definition of iterated function system, you can suppose that from some moment on, if you iterate finitely many times, you get less than 1. Yes. So, okay, so here we looked at the given a subset E of n, we look at the truncated system. So look also at where n belongs to E. For example, Jn is equal J1 to n. So Jn is just the set of what? All irrational numbers where all entries, continued fractions entries, belong to the set 1, 2, and n. So this is in particular, Jn is a subset of badly approximable numbers. And in this case, it is true that the limit of Hausdorff dimensions is equal to 1. This fact is actually true for all iterated function systems, was proved by Dan Martin and myself. But Doug Hensley was able in 1991 show how fast Hausdorff dimension converges to 1, giving precise asymptotics. Now, we can actually generalize this result to many other systems via the theory of open dynamical systems, and we also obtained more general asymptotic with the work of joint work with David Simmons, Lior Fishman, and David Simmons. And here, always, this is what Hausdorff measure is finite and positive. This is because there is just iterated function system, so everything is fine. So this is so now we decided to look with Anna Zdunik what's going on to the numerical value of Hausdorff measure. Now, okay, if you look at conformal measure, the limit or weak limit of the conformal measures, which is called Mn, okay, weak limit of Mn is equal to 11. There is no problem. This is a conformal measure on the interval 0, 1. This is quite easy. But if you look at the weak limit, and I'm looking at Hjn of Jn, then the issue becomes much more complicated. Okay, we can get this numerical value of the Hausdorff measure. So for Hausdorff dimension, there are very nice dynamical methods because we have what? Remember, we have this thing, but the Hausdorff measure exists if and only if P of H is equal to 0, and Hausdorff dimension is equal to this infimum. If the system is regular, like a Gauss map, which is then this is just the only 0 of the pressure function. And pressure function is purely dynamical, is actually and related to the transfer operator, and you can use both dynamical and functional analytic methods to understand it. Hausdorff measure is much more resistant. So we look at this deeper level to understand badly approximable numbers and how the Hausdorff dimension asymptotically looks like. And let's see. Okay. No, I'm going in the wrong direction. So this is okay. So moment. Okay. So nevertheless, the key, the starting point is the following definition, the following way of characterizing Hausdorff measure of the set. You look at this for any metric space, and this H, okay, assuming that this is positive and finite, like for Jn, okay, then we look at these ratios, the diameter over normalized Hausdorff measure. So this is Hausdorff measure of the set F divided by the measure of the space X. And if we are in the dynamical situation, then this measure is just the conformal measure. Okay? And so this is where dynamics somewhat can be inserted into study the Hausdorff measure. And in the interval 0, 1, this formula takes on this form. Look, this is much more complicated than the definition, than the formula for the Hausdorff dimension given by Balance formula. It's somehow much more subtle. The whole idea to do it in the case of a finite iterated function system comes really from the seminal work of Lars Olsen. So we look at this. Okay, so this is and then we proved in Anna's Dunik that in 2016 that the limit of Hausdorff measures of this, I think you know what it means, right? Jn is the set where only n digits 1 through n appear, and Hausdorff measure is 1. Okay, this is the Hausdorff measure of the set of irrational numbers, fine. But we constructed an iterated function system whose limit set consisting of somehow infinitely many pieces like this, whose limit set has full Lebesgue measure, is dense and has full Lebesgue measure like the set of irrational numbers, but this limit of Hausdorff measure was smaller than 1. So the continuity is very subtle thing, depends on what you consider. Okay? So so this is not so straightforward. For Gauss method it happens. So then we asked ourselves later on, much later, what about the asymptotic of converging to 1? And then, okay, we studied the linear version of the Gauss map. Linear version means that these are linear maps such that this is what? This is 1/2, this is 1/3, this is 1/4, and so on. And the maps are somehow, okay, the maps are linear here. This linear version of the Gauss map. And for this linear version, this was already quite interesting, but we got precise asymptotic of what, together with Rafał Tryniecki and Anna Zdunik, what this asymptotic is. This is 1, and this is 1 over Lyapunov exponent of this iterated function system. Which can be
where this is linear, I don't know.
Oh, okay.
Place of such branches.
Okay. Let's see. Yeah. Okay. 0, 1/2. Okay. Here is 1, and this way. This is the first map. The second map is 1/3, and the system looks like this, and so on. Okay. Okay, you can make them increasing. It is easier to prepare this. This does not really matter for Gauss.
Of course, it is also for Gauss.
Okay, now.
It is not linear.
Okay, Gauss is not linear. So for linear, we have precise asymptotic. Okay, what it is 1, and therefore this is okay. And for the Gauss map, for real Gauss map, given by this formula, 1 over x plus n, we can show that this lower limit the same, but this lower limit is finite, while this lower is positive, while upper limit is finite, which is again quite nice calculation in itself, and uses some really strong results from the theory of open dynamical systems. So we use this open dynamics as a one step to really apply this not only for asymptotic of Hausdorff dimension, but also of Hausdorff measures. So,
Mariusz, may I interrupt you?
yes.
Then I think for Gauss map we have that lower limit is larger or equal than 1.
Instead of infinity, right? Yes.
So it's lower limit.
Here is 1. Sorry. Okay. Right. Moment. Okay, this 0 should be 1, greater than or equal to 1. Yes. Thank you, Anna.
Yes, exactly.
Yes, that's right. So we proved that, and okay, let's see. So this is now, let's see. I would like to speak about, conformal measures for rational and transcendental dynamics. Okay. There could be much more about iterated function system to speak about conformal measure and so on, but I say this is just selected survey of the results which somehow were of interest for me. So here, the definition is this. as I already gave, and you can, for those who are familiar with this transfer operator, is this just this fixed point of the dual transfer operator. And existence and no, questions that are important are about existence, no existence, and uniqueness of conformal measures. And for rational functions, this was done by Dennis Sullivan, as you already mentioned, for transcendental meromorphic function. Essentially, basically, the last word belongs to Krzysztof Urbański, Bogusława Karpińska, and Anna Zdunik, which is also here, and then also my some works with Janina Kotus and Volker Mayer, and let's see. So I think I will not keep this slide too long. This is just the definition of the Julia set, which I think all of you are familiar with. And so basic properties. So here are the just the pictures of Julia, of some selected Julia sets, also well-known pictures. This is for exponential family, and this still exponential family. Still exponential family, nice pictures. We know all these contour bouquets and straight brushes and so on. And they dimensions, this is Bogusia Karpińska work, but this is Karpińska paradox and so on. I think we all are familiar with that. And this is how Julia sets may look for Weierstrass elliptic functions. These pictures are, I think, due to Jane Hawkins. And here is how to construct conformal measure for let's see, for rational functions. If the entire, unlike the case of Kleinian groups, there is really nothing from inside. I mean, Misha Lubitsch and Minsky and so on, then later on gave such a possibility, but I'm talking about how it was at the beginning. So there is nothing like inside. There's nothing inside the sphere. The rational functions do not act. So we have to work on the limit set. And first, if the Julia set is the entire sphere, then just take the Lebesgue measure. It's conformal measure. Otherwise, look at something which resembles Poincare series, which Dennis Sullivan defined, and then let's see, delta f is this exponent, and divergence groups first, like where the series diverges at t being delta f, then converges, the same procedure as in the context of Kleinian groups, and we get conformal measure. So conformal measure always exists, but there are several problems. Is it unique? Does there exist another exponent? Does there exist another exponent for which conformal measure exists? Are these measures atomic? Are these measures not atomic? How they are related to the geometry? There is really a bunch of big problems that it raises. And so the method also of construction, another alternative methods of construction, the KV method. We started with Manfred Denker, and transfer operator method. This was Kurt McMullen and Volker Mayer, and basically thermodynamic formalism. And see here, first I would like to speak about maybe somehow the result of, just bring up the result of Barański, Karpińska and Zdunik, but you define the pressure just in this way as this series suggested. And furthermore, then this limit exists, and is independent of z outside of a set of Hausdorff dimension 0. And furthermore, topological pressure is equal to the hyperbolic.
Are you talking about what?
I'm talking about functions in class S.
You are talking about meromorphic functions.
Meromorphic functions in class S, spacer class S.
Because for rational, I
Yeah.
did it before.
Yeah. Yes, you did it before for rational functions. Yes. So for rational functions, yes. So I'm talking already about
Rational, it is not so easy. You need to find my curve joining two points Z, and that's it.
yes. Okay. And let's see. And here is a hyperbolic where the sets are repellers. And so, yes. So this was first following the results of Lasse. Okay. And then they also show that if the function is merely in class B, so the class S doesn't import, but the singular set is finite, class B, but it is bounded, to be really sure, then if this set is not zero, then the same holds for Z in this difference of sets. So J of F minus that. So this, we take them like what? Tail functions, if you remember Felix, in our paper for rational functions. Probably don't remember. Yeah. And still, Urbański, Karpińska and Zdunik in 2018 showed that if T is zero and the topological hyperbolic meromorphic function admits a conformal measure, then pressure is equal to zero. And in addition, and this is quite important, the set of actually conical points has positive measure. Right? So the points that do not escape to infinity. The points that escape to infinity are in some sense, okay, but only some sense, not always, dynamically insignificant, because no invariant measure, no finite invariant measure lives on them. Okay, so you cannot actually treat them with the methods of ergodic theory. They are interesting for many other reasons, but they show that if such a measure exists, then pressure is equal to zero. Okay, and they even were able to estimate what is the how fast the measure decay at infinity. Conversely, Meyer and Zdunik in 2019 show that there exists a meromorphic function. I already mentioned this result in class B with no conformal measure supported on the set of radial points. Okay, to be sure, radial points, these are those points that you take a ball, a spherical ball around them, and you can take you have a point. You iterate forward, take a ball of the fixed spherical radius, and there is a conformal pullback to this point, univalent pullback. Okay, so there is no measure supported on such set. And okay, this is the result. Okay, which prove that if f is either rational function or an elliptic function, then Hausdorff dimension, this exponent is equal to the Hausdorff dimension of the radial Julia set hyperbolic dimension infimum of such T. And and also actually we extended, we actually completed this also in our book. This result, the one case was left. And then conformal measures are all alphors for expanding rational functions or elliptic rational functions. And then exactly one conformal measure exists, one exponent and only one conformal measures. Now, if the map is sub-expanding or parabolic, then the picture becomes somewhat more interesting. There exist also conformal measures. There is a unique measure and at this dimension SF, but for T bigger than SF, there exist other conformal measures, and all of them are really supported on the inverse orbit of parabolic points or critical points. And so now, for parabolic points, conformal measure for parabolic rational functions. do we know what are parabolic rational functions? The definition is simple. The map restricted to Julia set is expansive, but it's not expanding. This one possible definition. Another definition, but this is the Julia set is parabolic if the Julia, and it is expansive, by the way, if and only if Julia set contains no critical point. And it is parabolic if and only if Julia set contains no critical point, but contains at least one rationally indifferent periodic point. So there are various definitions. And so the iconic example is the map Z goes to Z squared plus 1/4, and then we looked at the value of Hausdorff measure. We're interested only in the question whether Hausdorff measure is finite or positive or not, and it turns out that all of this depends just on one parameter, namely on Hausdorff dimension, okay? Only. So if Hausdorff dimension is bigger than 1, then Hausdorff measure is finite and positive, and this is the right geometric measure, but packing measure is infinite. This is the case, of course, for the map what? Z squared plus 1/4. I think I proved somehow already in early 1990s that Hausdorff dimension is bigger than 1. And Guillaume Havard gave some estimates of what this Hausdorff dimension is. And so if dimension is smaller than 1, the examples what are? Take a Blaschke products whose limit set is a Cantor set inside the limit circle. Then Hausdorff dimension is less than 1, or you take, I think, Z goes to Z minus 1 over Z plus N with some N, okay? Then packing measure is finite and positive, but Hausdorff measure is 0, vanishes. Okay? Packing measure is the right geometric measure. And if so this is this example, and if Hausdorff dimension is 1, then regardless of the somehow dynamical picture, both Hausdorff and packing measures are positive and finite, and both of packing measure is a constant multiple of Hausdorff measure, and of course then Hausdorff measure, like in this case, divided by its numerical value is conformal measure. So we really got these results, but by a very careful study of this ratio M of B Z R over R to the power H. This was the main tool to understand the Hausdorff measure and Hausdorff and packing measure, looking at its actually what is its lim sup and what is lim inf. So okay, so there is only now, I think, one slide left. Okay, for transcendental meromorphic case, as already mentioned, for the tangent family, the picture, the dichotomy is actually the same as for the parabolic rational functions. This is what was discovered by Krzysztof Urbański. For the exponential family, okay, we're able to show with Anna's Dunik that Hausdorff measure on each horizontal strip is finite, and in particular, the total measure is sigma finite, and this while the packing measure is roughly infinite. Okay, so for elliptic functions, Hausdorff measure is always bigger than 1. If you have no constant elliptic function, then the Hausdorff dimension is always bigger than 1. In fact, Hausdorff dimension is always bigger than 2q over q plus 1, where q is the maximal order of a pole. And for the parabolic case, only one case. For the parabolic case, always Hausdorff measure is the right geometric measure, while packing measure is always infinite. And for elliptic function, when we have sub-expanding case, then again both Hausdorff and packing measures are finite and positive, and one is a constant multiple of the other. So, okay, let's see. Let me stop at this moment and thank you very much for your attention.
Do you have questions?
Yes?
I have a question. I wonder, so say you have two-dimensional or complex one-dimensional graph-directed Markov system.
Two-dimensional, yes, yes. Yes.
And so conformal, well, basically just holomorphic maps in
Yes.
some regions. And we don't have strong open set condition, so if the images are allowed to touch themselves, is there some good condition or method for showing that the Hausdorff dimension is less than 2?
Oh, it's less than 2, yes, okay, yeah. Okay, actually, yes. Okay, Hausdorff dimension is always less than 2. Okay, Hausdorff dimension is, so this is in general, Hausdorff dimension is less than n. Okay, if you are in an n-dimensional space, if you have such a possibility, and you look at the first level, first level sets, and the closure of the union is not the whole seed set.
This is strong open set condition.
Right.
No,
there's no strong open set condition. This is actually a strong open set condition means that you have open set condition. Okay, you can have overlaps, but at least one point does not belong to the boundary. And this what I wrote here is a different kind. Okay, this is kind of different condition. So you have okay, for this case, you have this one and this property varies, and you get the full dimension. In this case, you get a smaller dimension, so just okay. And let's see. This one, yes?
Yes, thanks. But to clarify, the domain of the maps should be the same set? Or...
Okay, let's see. Okay, yes, I think this is certainly true for IFSs. Let's see. For graph-directed Markov systems, it may happen that first for graph-directed Markov systems, it may happen first that you get even the union will be dense, but after passing to another iteration, this property may fail. So here you should really assume that this that you get something such a some subset well inside for some iteration. Good point. Yes. Because incidence matrix may not allow you to do iteration, and you may lose you may lose space.
Some other questions? I will ask. Do I understand correctly that elliptic functions and iteration is like Gauss map? Because for Gauss you have first translation to be in unit interval, and then you divide unit interval into small intervals, each goes to something. Well, anyhow,
yes.
For elliptic you have
Gauss map. I mean,
for elliptic
for Kleinian Groups,
wait.
yes.
No.
I
see for elliptic as treating the whole plane as split into unit squares.
Okay.
And on each square you go to everything.
Sure. each
So-
fundamental domain is
Yeah.
moved,
This
mapped to
looks-
the whole space, yes.
This looks like Gauss map. You have small interval, you have interval and
Yeah, but you have critical points inside.
yeah, yes, so maybe it's hard.
Right. Right, so then you can think about it as a Gauss, okay, you mean something?
Anyhow,
You know, then maybe you have something, yes.
there is some similarity here. For elliptic, we have critical points.
Right. Right, and I'm not sure whether for general elliptic functions, the branches would be given by very nice closed formula. For Weierstrass function, perhaps yes, but actually I have not found anyone writing explicit formulas for a Weierstrass function.
Maybe there are explicit formulas for Weierstrass function.
No, for inverse branches of Weierstrass function.
No, but I'm not talking that deeply. I'm just I see some
Oh.
similarity between Gauss map, where you define. Okay, I will not.
No, okay,
But
sure.
picture. looks
No, I mean, all iterated function systems kind of are similar to Gauss map, right?
Yes, in some sense.
Right, so therefore I started with this example as the first
But
one.
elliptic is very difficult because little square is mapped to everything.
And may fall several times. But you can look at fundamental domains, and these fundamental domains are mapped with bounded degree always, depending on what is the degree of elliptic functions. And you should really don't think about squares, but fundamental domains like rhombus or squares could be also. Then they are square elliptic functions, and you have some similarity. There is very good Markovian property, I agree. But around critical points is not one-to-one. But for majority of these elements of the fundamental domain, it will be one-to-one indeed, because elliptic functions has only finite many critical values. And therefore for more.
Not one-to-one, but to the whole plane. No?
Yes, but for many.
Again, you factorize, and then again map to the whole plane and factorize to squares,
Yes, right.
etc.
No, I mean, if I will be interested.
For me, this picture appeared in the Urbański paper from '95, where he studied tangent, and
Yes.
then he again, instead of mapping from the whole plane, he factorized it to a tube. Mapped it from a tube
Yes.
to a square because it was not.
No, you factorize with a cylinder.
Because it is half elliptic, it is not.
Right.
elliptic.
Yes. For exponential function, you can do this too. Factorize to the.
That's right.
Yes.
So this is a general idea
Yes.
where there is some similarity to Gauss map.
I agree. Yes.
More questions?
Questions from online audience, maybe? Questions?
Yeah, if can I ask something? If you can hear me.
We hear you well.
Yeah. Okay. Maybe I don't know whether my microphone is. Oh, okay, my microphone is working. Okay. So can you scroll back a little bit to results with Anna Zdunik and the first person whose name I unfortunately forgot. It's from 2025. It's about branches of Gauss map or something like this, or linear Gauss map.
Okay. Yes, I will go there. Okay.
It was already.
Okay, 25. Yes, this was probably 25.
It says 2025.
It was Trejecki.
Right. Moment. This was.
Do it slow.
This was slow. Okay, here, yes.
Yeah, so, this is a Gauss map, and then you are computing a numerical value of Hausdorff
Matter.
of, yeah, this is Hensley.
For
And
half
then-
dimension is Hensley, yes. This result is Hensley. For half of dimension, Hn is half of dimension. Small.
Go forward 1 or 2 pages.
Okay.
Too fast.
Yes.
Yeah, this,
Oh,
this
here.
yeah, the one. Yes, this one. Sorry about this.
Okay.
Yeah.
Okay. Fine.
So, yeah, I think my first stupid question is what is Gn here?
Gn.
Yeah,
Moment.
it's on the first theorem. It says H.
Mariusz, Jn. Just enter.
Oh, this one.
Probably I kind of don't.
Moment.
Well, there is a Gn in the
Jn?
first theorem. I just wondering what it is.
Oh, here, yes. Okay, for the linear version, Jn is the limit set of the linear Gauss map, where you have only and the contractions say okay phi 1, phi 2 through phi n.
Okay.
This is for linear version. Okay, I denoted the same letter, but actually probably let's see. Probably here should be, I should put maybe JLN to indicate that this linear. And actually, to be sure, this HN and that HN are different. For linear, for the linear Gauss, Hausdorff dimension is different, although a version of Hensley results still holds for linear version, is even easier. And the biggest enemy to jump from this case to this case is really the lack of distortion, and actually what is really the enemy that you cannot go, there are two enemies, but you have the distortion is not one, and you cannot jump from any scale to the large scale.
Okay, and so
Unlike, say, for a finite IFSs where you can do that, or conformal expanding repellers. Two main enemies. Gauss map has good distortion, but still it has no zero, and it actually somehow continues and preserves. Yes, Paulina, more questions?
yeah, so my second question was actually what is the constant kappa here?
Oh, kappa. Okay, kappa is actually, you can view it in various ways, two ways. Okay, one way is that you take, if you have a linear Gauss system, right? Okay, linear Gauss system.
Is it a number to begin
Okay,
with?
moment. If you have linear Gauss system, you can take you can look at the global map such that on every interval, this is like for the Gauss map, you can do global map and then calculate integral of the logarithm of the modulus of the derivative against Lebesgue measure. This is Carl. Just Lyapunov exponent of the system. Okay, or you can do it also in the on the symbolic level. And then it will be logarithm of modulus of the derivative of phi prime omega 1 composed with pi of sigma of omega, and against the let's see against the measure on the symbol space.
So, but is it right to think about it as a Lyapunov exponent of the system?
Yes, yes, this is Lyapunov exponent of the system. This is how it is. How it is, for example, defined in my book with Dan Morgan, which I think you know to some extent. There is exactly this Lyapunov exponent from the book for this just general Lyapunov exponent for the iterated function system.
Okay, so this is.
Okay, I could write the formula, but I think I now don't have my laptop buttons, and you would not see it. Okay.
Yeah, no, I'm just.
I say, but this is a lot. You invert inverse branches to get piecewise a piecewise holomorphic map of the interval 0, 1 and call this map say T, and they look at T prime on the and then logarithm of the modulus of the T prime and integrate against the back measure. This is what you can think here, but you can think more in the second symbolic interpretation, which is which calls for all iterated function system or even graph-directed Markov systems.
Thank you. Can I ask another question, or is everybody wants to go and have lunch?
Felix is
Go
not
on,
hungry
go on.
yet. You can ask.
Alina, go
Okay,
on, go
go
on.
ahead. No, go ahead, please. Yes. We have-
Okay, I can go and ask another question. So in the beginning, like much earlier, when you were discussing group actions on Bn, which I presume is n-dimensional ball, and you said that you work with generalization of Kleinian group. So is there a kind of nice example to have or to think about, or is it just because it's like that's basically the question, like, because the condition you said that you have about Poincare series, it's probably
Right.
not very easy to check immediately. So my question is basically whether you can give some example to think about.
Yes. Okay. I think the simplest Fuchsian groups and
No. I mean, so I want the case when n is bigger than 3. I understand that. I understand.
N can be
Okay.
any number. Sure. Take any Schottky group in any dimension. Finitely generated Schottky group.
Oh, okay.
Okay, Schottky group. You know how they are defined?
Yes, okay. So
I
you
think
can
in the Billman's book there is defined Schottky group, although I'm not quite sure, but that they are the simplest Schottky, the simplest Kleinian groups. And you can define them in any dimension. You take a collection of pairs of disjoint spheres and take the map from one somehow of the unit ball, preserving it, from which maps one of the spheres to the other. And these are just the generators of the Kleinian groups. And you can do actual calculations with them. There's very nice class of groups. Limit set are always kind of truly conformal expanding repellers, in the very sense of this word, if the group is finitely generated.
Okay, so basically, the construction from 2 dimensions, when you just have exactly group generated by maps
In 2
between.
dimensions has nothing special. I mean, 1 dimension was special because this was just the first word of Patterson, but then Sullivan didn't extend it to dimension 3, but to any dimension, already for all discrete groups. Dimension 3 is not so much distinguished.
Okay. So, but what you're saying is that like the construction just transfers to any dimensions that you can.
The whole field transfers to any dimension. And even actually with David Simmons and Tushar Das, we extended this construction to Hilbert spaces. I could talk again about this topic, about the so-called dynamical geometrical rigidity, which we then proved. This also, but there is not the time really now to discuss it. Yes, but there is no dimensional type obstacle. I mean, in the beginning, people really did. Studied one dimension, Fuchsian group and Kleinian groups in 3 dimensions, looking at, but this was really, this is like 19th century or early 20th century approach. Later then, they started to work on any dimension. So, and this is good. And Poincare metric has no restriction to, no dimensional restriction.
Yeah.
Yes.
And okay, so very short question. I was actually got worried at the end because I was expecting that Sullivan dictionary is going to appear, but it didn't appear because you started with groups and then you moved developing theory for the holomorphic functions. Is there yeah.
Okay, yes, you can view this okay in the sense of Sullivan dictionary, but Sullivan dictionary is actually great and is a good motivation of work. For example, it really motivated my work on especially parabolic rational functions. But but there is there is no direct bijection, and especially there is no bijection about the methods and ways of proofs. So yes, so you can say yes, there are similarities between the theory for rational functions and Kleinian groups, the definition of conformal and iterated functions too. This will be the third and graph-directed Markov system, the additional piece to Sullivan's dictionary. And all of them results can somehow motivate each other, and it's good. That's right. And Sullivan's dictionary has also some other ideas beyond measures and beyond fractality.
Yeah. Well, okay. Thank you very much. And I also can add that I heard a talk from your student or your former student, Jason Atnip, this morning, and he asked me to say hi.
Okay,
so I'm saying hi.
Yes, yes, thank you. Say hi to him. Yes, thank you very much. I also read him.
Okay.
Okay, thank you. Time for lunch. Not for everybody.